In this video, we'll go through some practical examples of calculating Hamming code and how it all works. So just a reminder about the bit positions of where we're laying things out. In 7.4, which is what we've got here, bit position 1 is going to correspond to P1, bit position 2 will be P2, bit position 4 will be our P3, and our other ones, 3, 5, 6, and 7, will be our data bits 1, 2, 3, and 4. Now we could extend this out to Hamming 1511. For this example, we're just looking at Hamming 7.4. So here's our first one. We've got this message that we're sending in binary. So what we can do is we can transpose that directly into our table down here, and we can write them down there. So we see that parity bit 1 will be a 1, parity bit 2 will be a 2, parity bit 3 will be a 1, and we've got our data bits there listed as well. Now what we can do is we can calculate and do our parity computations for each of them. So for parity bit 1, it consists of 1, 3, 5, and 7, those bits. So this one, this one, this one, and this one. So P1 plus D1 plus D2 plus D1 equals 3, which is an odd number. So we know that there's some sort of an error with one of those bits, 1, 3, 5, or 7. Then we go to parity bit 2. Now that consists of these two, 2 and 3, and 6 and 7. So that's where we'll be writing it. P2 is a 1, D1 is a 1, D3 is a 0, and D4 is a 1, which gives us 1, 1, 0, 1. It's odd again, so we know something's wrong with that. We then do the final one, which is bits 4, 5, 6, and 7. So 1, 0, 0, 1. I'm just looking at those ones there. That's even, so that one's okay. So we know that there's something wrong in both of those ones, and we look for what's common between both of those ones. If we look at them, the only thing that's common between them is this term here, D1. So data bit 1 or bit 3 is the one that's in error, because that's the common one between each of those that's generated the error in both of them. Here's another example. Here we've got a different binary number that we're sending, so we once again put that down here and we do our same calculations as before. So P1, D1, D2, and D4, and that gives us even this time, so that's good. Our next one, 2, 3, 5, and 6 will give us 1, 1, 1, and 1. That's even as well, that's good. But our final one, these last 4 bits, gives us 1, 0, 1, 1, which is an odd number, so that one's in error. So now what we want to do is look at what bit only corresponds to that last parity bit calculation. And if we look at them, it's bit 4, which is parity bit 3. So we know that this bit, bit 4, is in error. One more example on this idea. We'll take that number there and put it down here. And when we compute this one, what we actually find is all of them are in error. So 0, 0, 0, 1, that gives us a 1. We've got, when we take that one and that one, gives us 1, 0, 0, 1. That's an error as well. And finally, if we take these last 3, 1, 0, 0, 0, 1, 0, 1, 1, that's odd as well. So which one's in common between all of these? Well, it's this one here, bit 7. So D4, or bit 7, is the one that's in error. There's actually an alternate way we can work out, besides doing all that, working out which one's common between each one, to work out which particular bit's in error. And what we do is we put our parity bits in order, and we write them as a 1 or a 0 based on if there's an error in that parity computation. And so if there is an error, we assign a 1 to it. If there's no error, we assign a 0. And then we can just read it off as a binary number. So this was our first example before. We had error, error, no error. So if we write that as 110 and we write it as 011 like that, that's equal to 3 in decimal, and it was bit 3 that was the bit that was in error. Let's have a quick run through the other ones. This one was good, and an error there, so 100, and this one was bit 4 that was the one that was in error. And if we remember the last one, they were all in error. So 111, and if we say, look at that binary value, that's bit 7. And remember, bit 7, or D4, was the one that was in error for that one. Now, the other computation that we can do with our Hamming code is actually on the sender end, before we actually send what we're going to send. And that's where we have to work out what our parity bits should be, not what they were and whether there was an error or not. And we can do that very easily. We work out what bits we're concentrating on for each of those. So parity bit 1 will be adding bits 1, 3, 5, and 7, as we did before. And based on that, we can say, well, bit 3 is that, bit 5 is that, bit 7 is that. Well, what does parity bit 1 need to be? In this case, it will need to be a 1, and so on for all of the other ones. You could change those values to anything you want, and we're trying to encode this message. You put a different message in, it will tell you what parity bits you need out there at the other end. And so when we compute it, we can fill out our table as 1, 1, 1, and this will be all ones. So there goes a few different examples how we can calculate Hamming code and work out the different parity bits and work out where an error and localize that error within our code.